Okay, welcome to DT tutorial. In this video, we'll look at the laws of electrolysis. The laws of electrolysis. So, Michael Faraday in 1883 conducted some experiments that led to the postulation of the laws of electrolysis. And the laws of electrolysis are the first law of electrolysis and the second law of electrolysis. So, this is Michael Faraday. Like I said, Michael Faraday in 1883 he conducted some experiments, some electrolytic experiments that led to the formulation of the two basic laws of electrolysis. And the laws are the first law of electrolysis and the second law of electrolysis. So because of his remarkable work in electrolysis and electricity, he was referred to as the father of electricity. He did remarkable work in electricity and also in electromagnetism. So Michael Faraday to date is still referred to as the father of electricity. So this is very important. So like I said, Michael Faraday in 1883 conducted some series of experiments that led to the formulation of the laws of electrolysis. And the laws are the first law of electrolysis and the second law of electrolysis. So let's look at the first law. The first law of electrolysis states that the mass of an atom, it states that the mass of an atom liberated during electrolysis is directly proportional to the quantity of electricity passing through it. The mass of an atom that is liberated during electrolysis is directly proportional to the quantity of electricity passing through it. So this is a mathematical representation of the first law of electrolysis. It states that the mass of an atom, so the M here is the mass of the atom. It states that the mass of an atom liberated during electrolysis is directly proportional to the quantity of electricity passing through it. So that means that the higher the mass of the atom liberated, the higher the quantity of electricity that is applied. And the higher the quantity of electricity that is applied or that is passing through the electrolyte, the more the mass that will be liberated. So these two are proportional. As one increases, the other increases. So this is what Faraday's first law of electrolysis is all about. It states that the mass of an atom liberated during electrolysis is directly proportional to the quantity of electricity passing through it. So Faraday's first law of electrolysis states that the mass of an atom liberated during electrolysis is directly proportional to the quantity of electricity passing through it. So like I said, the more the mass, the more the quantity of electricity that will be required to pass through it. So this is the mathematical representation of Faraday's first law of electrolysis. So the mass M is directly proportional to the quantity of electricity Q. M is directly proportional to Q. M is the mass of the atom while Q is the quantity of electricity passing through it. So knowing that Q is equal to IT, the quantity of electricity is equal to current times time. This is the formula for finding the quantity of electricity. Quantity of electricity is equal to current times time. So knowing that Q is equivalent to IT, if we put the value of Q here as IT, our M will be directly proportional to IT. So M, the mass of the atom liberated during electrolysis, is directly proportional to IT. And I is current, T is time. So it's directly proportional to the product of the current times time. So to remove this sign of proportionality, what we'll do is to bring in a constant E. So by bringing in a constant, our equation will now become M is equal to EIT. EIT, where M is the mass of the atom that is liberated during electrolysis, the I is the current passing through the electrolyte during electrolysis, while time is the time taken for the current to pass through it, while the E that we have here is the electrochemical equivalence of the atom. So this is the electrochemical equivalence of the atom. So Michael Faraday's first law of electrolysis, like we said, states that the mass of the atom liberated during electrolysis is directly proportional to the quantity of electricity passing through it. And this is a mathematical representation of this law, that m, which is the mass of the atom liberated during electrolysis, is directly proportional to the quantity of electricity. So like we said, quantity of electricity is equal to IT. This is the formula for it. So we can also say that the mass of the atom liberated during electrolysis is directly proportional to IT, which is equivalent to Q. So to remove this sign of proportionality, what we'll do is to bring in a constant. So by bringing in a constant, our M will now be equal to EIT, where the E is the electrochemical equivalence of the atom that is liberated, I is the current that is passing through the electrolytic cell, while T is the time taken for the current to pass through the electrolytic cell. So this equation is very important and we will use it to solve questions later. Faraday's second law of electrolysis states that if the same quantity of electricity is passed through different electrolytes, if the same quantity of electricity is passed through different electrolytes, the masses of the ions deposited at the electrodes are directly proportional to their chemical equivalent. So the law states that if the same quantity of electricity is passed through different electrolytes, the masses of ions deposited at the electrodes are directly proportional to their chemical equivalent. So let's say this is an electrolyte and this is another electrolyte. So let's say this is electrolyte 1 and this is electrolyte 2. So if the same quantity of electricity is passed through these two different electrolytes, let's say the same quantity of electricity is passed through these two different electrolytes, the masses of ions that will be deposited at the electrodes will be directly proportional to their chemical equivalent. And we're going to explain this concept. So one thing you must know is that the minimum quantity of electricity required to liberate 1 mole of a singly charged ion, such as hydrogen ion and chlorine ion, is 96,500 coulomb. The minimum quantity of electricity, the smallest quantity of electricity that is required to liberate 1 mole of a singly charged ion. And examples of a singly charged ion, they are hydrogen ion and chlorine ion. They have only one charge, just one positive charge, and chlorine is having just one negative charge. So the minimum quantity of electricity required to liberate 1 mole of this singly charged ion, such as hydrogen ion and chlorine ion, is 96,500. So this is hydrogen ion. So a hydrogen ion as a singly charged ion will require 1 electron of electricity to be able to liberate 1 mole or 1 atom of hydrogen. The same thing with silver. Silver is an example of a singly charged ion. So as a singly charged ion, it will require 1 electron of electricity to be able to liberate 1 mole or 1 atom of silver. So, and 1 electron of electricity, like we said, is equivalent to 96,500 coulomb. The minimum quantity of electricity required to liberate 1 mole of a singly charged ion, such as hydrogen and chlorine ion, is 96,500. So hydrogen ion as a singly charged ion will require 1 electron of electricity, which is equivalent to 96,500 coulomb, to liberate 1 atom of hydrogen. Same thing with the silver. Silver as a singly charged ion will require 1 electron of electricity, which is equivalent to 96,500 coulomb, to be able to liberate 1 mole or 1 atom of silver. So this is very important. Then in addition to this, like I said, 1 electron of electricity is equal to 96,500 coulomb. 2 electrons of electricity will now be equal to 96,500 coulomb times 2, which will be equal to 193,000 coulomb. So if 1 electron of electricity is equal to 96,500 coulomb, 2 electrons of electricity will be equal to 96,500 coulomb, which is the value of 1 electron of electricity times 2, and that will give 193,000 coulomb. So having known this, like I said, the minimum quantity of electricity required to liberate 1 mole of a singly charged ion, such as hydrogen ion and chlorine ion, is 96,500 coulomb. So for an ion like copper ion that is having 2 positive ions, it will require 2 electrons of electricity to be able to liberate 1 mole or 1 atom of copper. So, and these 2 electrons of electricity will be equivalent to 96,500 coulomb times 2, and that will be equal to 193,000 coulomb of electricity. So, copper is a divalent element. It's a divalent element. So, as a divalent element is having 2 positive charges. So, for it to liberate 1 mole of copper or 1 atom of copper, it will have to accept 2 electrons of electricity. As it accepts these 2 electrons of electricity, it will liberate copper atom or 1 mole of copper. Then for a trivalent element like aluminium that is having 3 positive charges, it will require 3 electrons of electricity to be able to liberate 1 mole of aluminium atom or 1 mole of or 1 atom of aluminium. And like I said, 1 electron of electricity is equal to 96,500 coulomb. 2 electrons of electricity is equal to 96,500 coulomb times 2, which is equal to 193,000 coulomb. Then 3 electrons of electricity will be equivalent to 96,500 coulomb times 3, which is equal to 289,500 coulomb. So for a trivalent element like aluminium that is having 3 positive charges, it will require 3 electrons of electricity, which is equivalent to 289,500 coulomb to be able to liberate 1 mole of aluminium. And copper, which is a divalent element, will require 2 electrons of electricity, which is equal to 193,000 coulomb to be able to liberate 1 mole of copper or 1 atom of copper. So this concept is very important, and we are going to apply this as we move further. So like I said, Faraday's second law of electrolysis, it states that if the same quantity of electricity is passed through different electrolytes, the masses of ions deposited at the electrodes are directly proportional to their chemical equivalents. If the same quantity of electricity is passed through different electrolytes, the masses of ions that will be deposited at the electrodes are directly proportional to their chemical equivalents. So let's assume that these are 2 different electrolytes. This is electrolyte 1 and this is electrolyte 2. So what Faraday's second law of electrolysis is trying to say is that if the same quantity of electricity is passed through these 2 different electrolytes, the masses of ions deposited at the electrodes will be directly proportional to their chemical equivalents. So this is the anode, this is the cathode, this is the anode, and this is the cathode. So if the same quantity of electricity is passed through these 2 different electrolytes, the masses of ions deposited at the electrodes will be directly proportional to their chemical equivalents. And by chemical equivalents, we are simply talking of the charges they are carrying. We are talking of the charges they are carrying. So to take us further, let's look at this 2014 JAM question 25. The question is, how many Faraday of electricity is required to produce 0.25 moles of copper? How many Faraday of electricity is required to produce 0.25 mole of copper? So A, we have 1 farad, B, we have 0.01 Faraday of electricity, C, we have 0.05 Faraday of electricity, and D, we have 0.5 Faraday of electricity. So how many Faraday of electricity is required to produce 0.25 moles of copper? So like what we've discussed before, copper is an example of a divalent element, So copper as a divalent element, it is having two charges. So it will require two electrons of electricity to be able to liberate 1 mole of copper or 1 atom of copper. So these two electrons of electricity is also equal to 2 Faraday of electricity. So in other words, 2 Faraday of electricity will liberate 1 mole of copper. 2 Faraday of electricity will liberate 1 mole of copper. So the question is, how many Faraday of electricity will be required or is required to produce 0.25 mole of copper? So we cannot say that X Faraday of electricity will liberate 0.25 mole of copper. 0.25 mole of copper. So I haven't written it out like this. You can just cross multiply and get your answer. So that means X Faraday of electricity, that is X times 1 will now be equal to this 2 Faraday of electricity, 2 times 0.25. So X times 1 is X. 2 times 0.25 will be equal to 0.5 Faraday. So that tells us that 0.25 moles of copper will be liberated by 0.5 Faraday of electricity. So this is our answer. Our answer is 0.5 Faraday of electricity. So how many Faraday of electricity is required to produce 0.25 moles of copper? So it is not 1 farad, it is not 0.01 farad, it is not 0.05 farad. The answer that we got is 0.5 farad. So this is the correct answer to this 2014 JAM question. The next question that we have here is a 2015 JAM question, and it's question 49. And the question is, calculate the mass of magnesium that will be deposited by 8 Faradays of electricity, given that the relative atomic mass of magnesium is 24. So A we have 96 grams, B we have 48 grams, C we have 72 grams, and D we have 120 grams. So what mass of magnesium will be deposited by 8 Faradays of electricity, given that the relative atomic mass of magnesium is 24? So again, the question is, calculate the mass of magnesium that will be deposited by 8 Faradays of electricity, given that the relative atomic mass of magnesium is 24. So what we're looking for is the mass of magnesium that will be deposited by 8 Faradays of electricity. And we're given that the relative atomic mass of magnesium is 24. So the first thing I want to identify out here is that magnesium is a divalent element. So as a divalent element, magnesium, it belongs to group 2 of the periodic table. So that makes it a divalent element. So as a divalent element, it will require 2 electrons of electricity to liberate 1 mole of magnesium. So this is 1 mole of magnesium. And you know that 1 mole of magnesium is equal to 1 mole of magnesium is equal to 24 grams of magnesium. This is the relative atomic mass of magnesium, and this is the relative molecular mass of magnesium. So 1 mole of magnesium is equal to 24 grams. This is very important. It's from the fundamentals of chemistry. You must have known this before now. So magnesium is a divalent element because it belongs to the group 2 of the periodic table. It will accept, or it will require 2 electrons of electricity to liberate 1 mole of magnesium, which is equal to 24 grams. So like I said, 2 electrons of electricity is also equivalent to 2 Faraday of electricity. So 2 Faradays of electricity will be required by magnesium ion to be able to liberate 1 mole of magnesium, which is equal to 24 grams. So we now know that 2 Faraday of electricity is equal to 24 grams of magnesium. Then the question is 8 Faraday of electricity, because we are looking for the mass of magnesium that will be deposited by 8 Faradays of electricity. So 8 Faradays of electricity will now be equal to what mass of magnesium? So that will be X, we don't know. So having written this out like this, you can just cross multiply. So when you cross multiply this expression, this will now be equal to 2F times X, that is this 2F will multiply this X, that will be equal to 8 Faraday of electricity, which is this, times 24 grams of magnesium times 24 grams. So 2F times X will now be equal to 2Fx, which is equal to 8F times 24 grams of magnesium. So since what we're looking for is X, we will now make X the subject of the formula, and by making X the subject of the formula, we divide both sides of the equation by the coefficient of this X, so which is 2F. So my expression will now be X is equal to 8F times 24 grams all over 2F. So my F will cancel this F. 2 here is 1, then 2 here is 4. So what is left remaining is equal to 4 times 24 grams. And 4 times 24 grams is equal to 96. So my X is equal to 96. So the mass of magnesium that will be deposited by 8 Faradays of electricity is 96 grams. This is my answer, 96 grams. So what we did in this question is that we are looking for the mass of magnesium that will be deposited by 8 Faradays of electricity, and we're given the relative atomic mass of magnesium to be 24 grams. So like I said, magnesium is an example of a divalent element. So as a divalent element, it is divalent because it belongs to group 2 of the periodic table. So as a divalent element, it will require 2 electrons of electricity to be able to liberate 1 mole of magnesium. So, and 1 mole of magnesium is equal to 24 grams of magnesium. So in other words, and like I said, 2 electrons of electricity is equal to 2 Faraday of electricity. So that means that 2 Faradays of electricity will liberate 24 grams of magnesium. So, but the question is, what mass of magnesium would be deposited by 8 Faradays of electricity? So if 2 Faraday of electricity deposit 24 grams of magnesium, 8 Faraday of electricity will deposit X gram of magnesium, which we don't know. So having written out the expression like this, you can now cross multiply. So by cross multiplying, my expression will now be 2F times X is equal to 8F times 24, but there is no need to write all these values. So it will now be equal to 8F times 24 grams. So my X now will now be equal to 8F times 24 grams all over 2F, because we are dividing both sides of the equation by the coefficient of this X, which is 2F. So this F will cancel this F. 2 here is 1, 2 here is 4. And 4 times 24, what is remaining is 4 times 24 grams. So this 4 times this 24 grams will now be equal to 96 grams. So the mass of magnesium that will be deposited by 8 Faraday of electricity is actually 96 grams. So the correct answer to this question 49 of 2015 JAM question, the correct answer is 96 grams. So in summary, we have looked at the first and second law of electrolysis, and we said that the first law of electrolysis states that the mass of an atom liberated during electrolysis is directly proportional to the quantity of electricity passing through it, and we said that this is the mathematical representation of this law, that the mass of an atom liberated during electrolysis is directly proportional to the quantity of electricity passing through its Q. And also we stated second law of electrolysis. And Faraday's second law of electricity states that if the same quantity of electricity is passing through different electrolytes, the masses of ions deposited at the electrodes are directly proportional to their chemical equivalent. And we've also analyzed this concept as well. In the next video, we'll continue with the calculations on electrolysis, and we'll be looking at this number 25 JAM question in the year 2010.